So, hello everyone. Now, in this class, I am discussing one more chapter of your physics, that was your oscillations. Okay. Firstly, I will give you a short revision about the topic oscillation. Then I will discuss the previous year questions of oscillation. Now, first in oscillation motion, there is periodic motion. Periodic motions. So, which type of motion are known as the periodic motion? A motion which repeat itself again and again is known as the periodic motion. A motion which repeats itself again and again and again in a regular interval of time, in regular interval of time are known as the periodic motion. Like motion of a minute hand of a clock, motion of a planet around the sun, and like you are going to school and you are going to school daily. This is also periodic. You are coming to class daily. This is also periodic. All that are motion which repeats itself in a regular interval of a time are known as the periodic motion. For first example, as motion hand of a clock, motion of minute hand of a clock, motion of minute hand of a clock. Second one is motion of planet around the sun, motion of planet around the sun. All these type of motion are known as the periodic motion. That means which repeat itself in a regular interval of a time. Suppose this is the sun and this is our planet. So that will repeat itself again and again to this position. This is known as the periodic motion. Now, second is known as oscillatory motions. Second is oscillatory motion or oscillation. Oscillatory motion or oscillation. So, what is oscillatory motion or oscillation? The to and fro motion of an object is known as the oscillations. Okay, the to and fro motion, the to and fro motion of a pendulum is called oscillatory motion. Is called oscillatory motion. For example, suppose this is a pendulum, so it will repeat its position again and again. This motion is known as the to and fro motion. Okay, so this is known as the oscillatory motion. Example of oscillatory motion are swing, pendulum, etc. Now a statement is come. Statement has come. So all periodic motion, so all sorry, all oscillatory motion, all oscillatory motion are known as periodic. All oscillatory motion are periodic, but all periodic are not oscillatory. But all periodics are not oscillatory. So what is this statement? Now I am taking an example. Suppose this is a pendulum. So it will repeat again and again at its position. It will do a to and fro position, to and fro position. Okay, to and fro motion. So if it was doing to and fro motion, that means it is doing oscillation. And what the oscillation means, it will repeat its position again and again. So all the oscillation motion are known as periodic motion, because all oscillation motion repeats its position. What is to and fro position? To and fro means they are moving like that. Means they are repeating a position, particular position again and again. Okay, this type of motion is known as the oscillatory motion. Okay, but all periodic, example, that this is sun and a planet revolve around it in a circular orbit, so it will move only in this direction. Suppose it is moving in anti-clockwise direction, but they does not repeat its position again and again. It was not doing the to and fro motion. That's why all periodic motion are not oscillations. Okay, understand? The all periodic motion are oscillation. All oscillation are periodic motion, but all periodic are not oscillations. Okay, so in oscillations, there are two types of motion. First is known as the simple harmonic motion, and second one is known as anharmonic oscillation. So what is simple harmonic motion? Oscillation is the to and from position. So it will come at this position. So this is known as the oscillation, means to and fro position. But in a SHM, there are two type of oscillation. First is simple harmonic motion, and second is an harmonic oscillation. Simple and harmonic oscillation or an harmonic motion. So what is simple harmonic motion? If it maintains its energy during the motion at any time interval, or you can say that its time period and amplitude will be same, so this is known as the simple harmonic motion. But anharmonic motion are which can decrease with time, which can decrease its energy with time, or which does not have a constant amplitude. So that's why it's known as M harmonic motion. First round it will come to this position A, in second and at position B. After that it will come as position C at D. After again motion, it comes at position P and Q. So this type of motion is known as an anharmonic motion, means in which the energy is decreases with time. So that motion are known as the anharmonic oscillation, and in which energy remain constant during the motion. So this type of motion is known as the simple harmonic motion. Now again, all simple harmonic motions are oscillatory, but all oscillatory are not simple harmonic motions. That all SHM are oscillatory motion, but all oscillation, all oscillatory motion are not simple harmonic motion, are not simple harmonic motion. So these are the examples, because all SHM are a part of SHM is also part of oscillation. So that's why all SHM are oscillatory motion, but all oscillatory motion are not SHM, because oscillatory motion also have SHM or an harmonic oscillation. That's why all oscillatory are not SHM. Now consider the condition. This is the pendulum. This position is known as its mean position. Mean position means a position where its displacement we considered zero, because it is at its rest position. Now it come to at this position, which is known as its extreme position. Okay, this is also known as its extreme position. Extreme position. So extreme position is that in which the value of x is equal to plus minus a. Plus minus a. A means its amplitude. X is equal to plus minus a. Okay, either it is plus a or minus a, and if it is plus a, then this position is, if it is plus a, then this position is at minus a, and if this position is at plus a, this position is at minus a. That's why I am writing plus minus a. So extreme position is the maximum position till where the particle, till the pendulum can move. Okay, so this motion is known as the this motion is known as the oscillatory motion or simple harmonic motion. This position is known as the mean position. Mean position are the position where we consider displacement to be zero, and the extreme position are the position which are which where the displacement is not zero. the displacement is equal to plus minus of amplitude. So what happen if a body comes to that position? So what will happen? A force will tends toward its mean position. Now when it goes to position number B, so what will happen? A force tends its to tends to move it at its mean position. Okay, when the particle goes to point A, a force come in a backward direction, it will tends its to come at its mean position. Now, when this force when it will come at position O, so the speed will increase. So after increasing its speed, it will go to position B, and a position B again a force is come which will tend its toward downward. So what this force is not, so that this force is always directly proportional to x, where x is its mean position, because it always tends to move the particle at its position. So when we remove, we get a sign of proportionality minus k x की power n. F is directly proportional to x की power n, mean position at any times. Okay, so this is known as the F is equal to minus k x की power n. Okay, always forces always acts toward mean position, acts towards mean position, mean position. Next, negative sign, negative signs show that force and the motion of a particle both are in opposite direction. Both are in opposite direction. Okay, so force is directly proportional to x की power n is the real equation. So when we remove the proportionality, a constant is came which is known as the minus k. So we are discussing here the SHM. In SHM, SHM is also oscillatory. So the condition of force for oscillatory is minus k x की power n. But in SHM, put n is equal to 1. So we will get F is equal to minus k x. So this is the value of force in SHM. Okay. So these are the value of SHM. Now consider the force. Find the value of force at mean position or extreme position. At mean position, x is equal to 0. Now at mean position, if x is equal to 0, so put the value of x in here. So you will get force is equal to 0. So at mean position, no force will be act. Now next, at extreme position, at extreme position, x is equal to plus minus a, or you can say that mod x is equal to a. So put the value of mod x, you will get the value F is equal to minus Ka. So at extreme position, force will be minus Ka, or the magnitude of force will be K times of A. Okay, where K is a spring factor. You can say the K as spring factor. Spring factor or proportionally constant. Yeah? Maybe it is proportionally constant. It is defined as the restoring force constant. Restoring force constant. Now clear, in SHM, we have discussed that f is equal to minus of kx, f is equal to minus of kx. Now finding the acceleration in SHM. Now how we can find the acceleration? We know that f is equal to minus k times of x, and this is equation first. And according to second law of motions, Newton's second law of motion is force is directly proportional to rate of change of momentum. After solving it, we will get a formula F is equal to ma. Newton's second law of motion, F is equal to ma. This is equation second. So from equation first and equation second, they both have equal LHS. So they have both equal RHS. M equal to minus kx, so A is equal to minus k upon m of x, where k upon m is omega square, where k upon m is equal to omega square. So the value of A will be minus omega square x. So this is the value of acceleration, where omega square is equal to k by m, or omega equal to under root k by m. Okay, so this is the value of omega under root k by m. Now the value of A is minus omega square x. A is equal to minus omega square x. Now find the value of at mean position and at extreme position. So at mean position, the value of x is equal to 0. So if we put x is equal to 0 here, so the value of A will be 0. So at mean position, acceleration will be 0. At extreme position, at extreme position, x is equal to plus minus of A is amplitude. So the value of A will be minus omega square A. Or if you take the magnitude, so you will get the maximum value of acceleration at mean position. Okay, so the maximum value of acceleration is at its mean position, which is equal to omega times of A, omega square times of A, where omega is k upon m, where omega square is equal to k upon m, or you can write simply omega as under root k by m. So this is the value of acceleration. Now I'm finding the value of velocity v. We know that acceleration is equal to minus omega square x. Acceleration is dv by dt is equal to minus of omega square x. Now multiply and divide by dx. So dv upon dt, dv upon dt into dx upon dx is equal to minus of omega square x. Now consider this part, dv upon dx one side and dx upon dt one side. So dv upon, I am multiplying divide dx and dx by numerator and denominator. Huh? That's why I will write dv upon dt into dx into dx. If I cut, so you will get 1, and 1 into dv by dt is dv by dt. So dv upon dx into dx by dt is equal to minus omega square x. Dx by dt is change in position with time, which is known as the velocity. So dv by dx into v is equal to minus omega square x. So v dv is equal to minus omega square x dx. So this is the value of v, but just wait, huh? 1 minute. So v dv is equal to minus omega square x dx. V dv is equal to minus omega square x dx. Now I am integrating it by 0 to v, and it by x is equal to a to x at any position x. So you will get v square by 2, 0 to v, and here you will get minus omega square inside x dx is equal to x from a to x. The value of integration x dx is x square by 2. So the value of x dx is x square by 2, from where a to x, and v square by 2 from 0 to v. So 2 will be cancelled by 2. So by putting upper limit, so v square minus 0 is equal to minus omega square times of x square minus a square. So v square is equal to, if minus sign multiply inside, so omega square is equal to a square minus x square. So the value of velocity will be under root of omega square a square minus x square. Now under root omega square will be omega, so v is equal to plus minus omega under root a square minus x square. So this is the velocity of this is the value of velocity. V is equal to plus minus omega under root a square minus x square. Okay. Now find the value at its mean position or at its extreme position. At mean position, x is equal to 0. So V is equal to omega a. V is equal to plus minus omega a, or you can find it as v maximum. Okay, so at mean position the value of velocity will be maximum. At extreme position, at extreme position, x is equal to plus minus a. Now if you put x is equal to plus minus a in the expression of velocity, you will get a square minus a square is equal to 0, and 0 into omega is also 0. So at mean position, the value of velocity will be 0. Okay, so that is the expression for velocity of uh, as a jump. Now second is energy in SHM. Energy in SHM. So there are two type of energy in SHM. First is kinetic energy, and second one is potential energy, and sum total of these is known as the mechanical energy in SHM. So firstly, we define the kinetic energy in SHM. Kinetic energy is half m v square. So the value of v will be omega plus minus, sorry, plus minus omega under root a square minus x square plus minus omega under root a square minus x square का whole square. So you will get the value of kinetic energy as half m omega square a square minus x square. Now m omega square. We know that omega square is equal to k by m. So k is equal to m omega square. So I can write in place of m omega square as k. So half k a square minus x square is known as the kinetic energy of SHM. Now next, the value of k is half k a square minus x square. So there are two main positions. First is at extreme position, and second one is at mean position. So at mean position, x is equal to 0. At mean position, x is equal to 0. So if you put x is equal to 0 in the expression of kinetic energy, you will get the maximum value of kinetic energy, which is equal to half k a square. And if you put the value x is equal to plus minus a in the expression, you will get the value of kinetic energy as 0, because half a square minus a square is 0. So at extreme position, kinetic energy is 0, and at mean position, the value of kinetic energy will be maximum. So this is the value of kinetic energy for. Next is potential energy. Potential energy. Potential energy is defined as a negative of conservative work done by the body. So du is minus of work done is an conservative work done by conservative body, conservative force. Okay, so du is equal to minus of work done is defined as the force into displacement, and the angle between them is cos 180 degree. Suppose I am giving you an example of it. Just a minute. Huh? Also, this is its mean position. This is its extreme position. Now suppose is at this point. If we apply force on it in this direction, sorry, if we move, displace it in this direction, ds, so force is always acts toward the opposite direction. So that's why that they both have opposite direction. That means the angle between them is 180 degree. The value of cos 180 is -1. So minus integration of f dx. And the value of force is uh, kx dx minus kx dx. Okay. Now, if k is came outside, so minus k integration of x dx, and x is equal to 0 to x is equal to x. So you will get the value minus x is equal to x square by 2, 0 to x. So minus half k x square is the value of potential energy. Now, at mean position, x is equal to 0. At mean position, x is equal to 0. So the value of kinetic potential energy will be 0 at mean position. At extreme position, at extreme position, x is equal to plus minus a. So u maximum is equal to half k a square. Okay. So that is the value of potential energy. Now next is total energy. Total mechanical energy. Total mechanical energy. So total mechanical energy is defined as the sum total of kinetic energy plus potential energy. Kinetic energy is half k x square, no, sorry, half k a square minus x square, half k a square minus x square, and the potential energy is half k x square. Now, if you take half k common, so you will get a square minus x square plus x square. X square will be cut, so you will get the value half k a square is the value of total energy. But this total energy is independent of x, which is independent of x. Okay. So this is the value of total mechanical energy. Now next is the graph between graph of total energy. So this is the graph. Now this position, this is the value of k. It is maximum at, sorry, it is 0 at mean position. So x is equal to a, and at x is equal to minus a. Is it 0? And this is the graph of potential energy. It is minimum, it is maximum at its mean position and minimum at its mean position. So this is the graph or graph between Ka and Pe. Pe and Pe. Now one more topic is here. Case is cleared. Differential equation of SHM is cleared. And now you have another topic. Something in the form of. Now, firstly, I'm discussing some question. First question is, give two example. Give two example of of periodic motion which are not oscillatory. Give two example of periodic motion which are not oscillatory. So the two example of periodic motion which are not oscillatory are the motion of planet around the sun and the motion of an electron around the nucleus. So the motion of planet around the sun, the motion of planet around the sun and the motion of electron around the nucleus, and the motion of electron around the nucleus. Next question is, define simple harmonic motion. Define simple harmonic motion. These all are your previous year question. Huh? Define simple harmonic motion. Give two example. So what is the definition of simple harmonic motion? A body is said to be in a simple harmonic motion if it moves to and fro along a straight line, but its mean position such that at any point is accelerated, its acceleration is proportional to its displacement, but opposite in direction is direct always toward the mean position. So this is the definition of simple harmonic motion, but any easier definition can be written. So simple harmonic motion. Wait, just a minute. So what is simple harmonic motion? A particle is said to execute is said to execute simple harmonic motion, simple harmonic motion if it moves to and fro about a mean position, about a mean position under the action of under the action of a restoring force, under the action of a restoring force which is directly proportional, which is directly proportional to its displacement, which is directly proportional to its displacement from the mean position, from the mean position, from the mean position, and is always directed toward the mean position, and is always directed toward the mean position. It is always directed toward the mean position. Okay. Now, example of simple harmonic motion are motion of a simple pendulum, motion of a simple pendulum. Next, motion of a mass attached to a string, motion of a mass attached to a spring, motion of atom in a solids, motion of atoms in a solid, cork floating on water, cork floating on a water. So these are the two questions. Now next is what happened to the energy of simple harmonic motion if its amplitude is doubled. So next question is what happens to the energy of a simple harmonic oscillator, energy of a simple harmonic oscillator if its amplitude is doubled, if its amplitude is double. Now we know that the formula of E is equal to half k a square. Okay. Now where k is m omega square. So if nu a dash will be 2 times of a, so nu a dash will be half of k a dash whole square. Means half k 2a square. So 2a square means 4 times of half k a square, which is equal to 4e. So e dash is equal to 4e is the value. Okay. Now next is what is phase? What is phase? Discuss the phase relation between discuss the phase relation between displacement velocity and acceleration in simple harmonic motion, in simple harmonic motion, simple harmonic motion. Okay. Now first is what is phase? So I am writing the phase. Phase is nothing but angle. Okay. The phase of a particle, the phase of a particle executing SHM at any instant, at any instant is defined, any instant is defined as its condition or state regards to its position regards to its position and direction of motion at that instant, and direction of motion at that instant. Okay. Phase is simply but angle, at angle is defined as the phase. Now, write the condition here. After that, I will derive the formula for it. Okay. So the first formula is for displacement. So displacement is equal to a times of cos omega t minus 5, where this omega t minus 5 denote the phase. So this is the relation between displacement and the phase. Second one is, after this question, I will derive the formula for it. Huh? Next is velocity. So the value of velocity is v is equal to minus a omega square sine omega t minus 5. Sine omega t minus 5. So this sine omega t minus 5 is known as the phase angle. So this is the relation between velocity and phase. Next is acceleration. Acceleration. So acceleration is defined as minus omega square a cos omega t minus 5. So this omega t minus 5 is defined as the phase angle which have relation with acceleration. Okay. So this is the phase. Now compare all the phase. The displacement have phase x is equal to a cos omega t minus 5. Velocity has phase a omega square sine omega t minus 5. Acceleration has phase minus omega square a cos omega t minus 5. Now convert all these phase into a same value. So x is equal to a cos omega t plus 5 will remain. Now this sign can be written in terms of cos as a omega square sine pi by 2 minus theta. So pi by 2 minus omega t minus 5. So I can write it as cos, because cos 90 minus theta is sine theta. So I am writing as sine omega t minus 5 as pi by 2 minus omega t minus 5. Right in the bracket, the cos pi by 2 minus theta is equal to sine theta. Okay. So that's why I have written it. So the phase difference between displacement and velocity is pi by 2. Now write this, if this minus sign come inside, so what I can write it as omega square a cos pi by pi plus theta, cos pi plus omega t minus phi, because cos pi plus theta come in third quadrant, and in third quadrant add sugar to coffee. 0 pi by 2 pi 3 pi by 2. So it will come in third quadrant, pi plus theta, where tan and cot is positive, whether all are negative. So cos pi plus theta is equal to cos minus of cos theta. Pi is even multiple of pi by 2. So that's why cos will remain in cos. So the phase difference between the displacement and the acceleration is of pi. Okay, clear? The phase difference between x and b is pi by 2, and the phase difference between x and a is pi. Now, the next question is derive the expression for. In this question, you will understand how the formula will come, how the formula has came of displacement, velocity, and acceleration. Describe the expression for displacement, velocity, and acceleration. Acceleration of a particle executes SHM. Executes SHM. Now consider the particle P moves on the circumference of a circle of radius r. Consider a particle P moves on the circumference of a circle, moves on the circumference of a circle, circumference of a circle of radius r, of radius r, uniform of radius a, sorry, circle of radius a, with uniform angular velocity, with uniform angular velocity omega, with uniform angular velocity omega, let Pn be the perpendicular, be the perpendicular drawn to diameter, drawn to diameter y dash from P. Okay, so this is the circle. Oh, wait, excuse me. Suppose this is the circle and this is a line y dash on it, and a line second x dash on it. Now particle is moving on a circle. This is the position of particle point P at an angle theta, at an angle theta. We know that omega equal to theta upon t, angular velocity is equal to angular displacement upon time. So theta is equal to omega times of t. So theta is defined as omega times of t. So the displacement of a particle is, suppose if I join this particle, this n is defined as the displacement y. The displacement of particle is in y direction, so I am denoting it by y. So the for in triangle ONP, in triangle ONP, sine theta is equal to this px is also known as OM. Px upon OA, OX or simply you can write px is similar to on. So I can write it as on, and ox is similar to np. I am writing it as np sin theta. Okay, sorry, this is perpendicular upon hypotenuse. Hypotenuse is op, so I can write it as op. Okay, so sin theta is equal to on upon op. So the value of on equal to op sin theta. On equal to op sin theta. On equal to op sin theta. So what is the value of on here? On is y. So y is equal to op. This is amplitude A. Consider this as amplitude A. So the value of on equal to A sin theta. A sin theta. And what is the value of on? On is equal to A. So y is equal to A sin theta. And what is theta? Theta is omega t. So I can write y as A sin omega t. So this is the value of displacement at any position. Now second, the velocity. Velocity is defined as v is equal to dy by dt. So d by dt of a sine omega t. A sine omega t. So a is outside. So d by dt of sine omega t. So sine omega t is defined as a omega t cos omega t. And I can write cos omega t as 1 minus under root 1 minus sine square omega t, because we know that sine square theta plus cos square theta is 1. So cos square theta is equal to 1 minus sine square theta. So cos theta is equal to under root 1 minus sine square theta. So I can write it as a omega t 1 minus sine square omega t. And what sine omega t from here? It is y upon a equal to sine omega t. No, you can write simply as a omega t is equal to under root 1 minus of sine omega square t. Okay, so this is the value of velocity for here, for it, that the a omega t and 1 minus sine square omega t. Okay, now next is acceleration. Acceleration is defined as dv by dt. A is equal to dv by dt. So a is equal d upon dt of a cos omega t. Capital A cos omega t. A cos omega t. So A times of d by dt of cos omega t is equal to minus sine omega t. So minus A sine omega t. This is the value of acceleration. So omega t equal to so these are the value of acceleration. So student, that's all for today. In next class, I will discuss about more question belongs to this question. Okay, that's all.